There's something odd about the region Voyager occupies right now. It isn't the space we read about in textbooks. It isn't the peaceful void people picture when they imagine the depths beyond our world, and it certainly isn't the comfortable zone within the sun's domain. It's a kind of edge that shouldn't feel like an edge at all. Yet everything drifting out there moves in ways that keep telling scientists this zone is far stranger than anyone anticipated. What makes it compelling is how hushed the probe itself has become. It's gliding through one of the most enigmatic corners of the solar system, more distant from its origin than any object humanity has ever sent into the darkness. And it's nearly soundless. No cameras transmitting images, no dramatic sensor bursts, just slow, methodical readings trickling in from equipment older than most of the people analyzing this information. And somehow those readings keep revealing things that contradict the straightforward model we once held of the sun's boundary. So the question becomes unavoidable. What exactly is unfolding out there? What is Voyager moving through? And why does this zone, which was supposed to be hollow and unremarkable, keep delivering scientists more mysteries than solutions? That's the territory we're about to explore. Across the past 5 decades, the twin Voyager spacecraft have revealed more than anyone imagined possible when they lifted off in 1977. They delivered our first intimate views of Jupiter's churning tempests, the volcanic fury of Io, the fractured ice plains of Europa, the unexpected rings encircling Uranus, the nitrogen geysers erupting from Triton, and the ethereal blue atmosphere shrouding Neptune. After departing the planetary realm, they continued their exodus and started transmitting readings from a section of the solar system no previous mission had ever touched. Voyager 1 accelerated faster and climbed upward, leaving the orbital plane of the planets behind. Voyager 2 followed a gentler, lower trajectory. As of November 2025, Voyager 1 is racing through the emptiness at approximately 17 kilometers per second, while Voyager 2 maintains a pace of roughly 15.3 kilometers per second. Velocities born from gravitational slingshots that now propel them relentlessly into the space between stars. At present, both have ventured beyond the heliopause. Voyager 1 sits at 169 astronomical units from the Sun, and Voyager 2 rests at 139 astronomical units, though not in identical surroundings. Voyager 1 has penetrated deeper into interstellar territory in a direction where the sun's grip weakens more abruptly. Voyager 2 pierced the threshold later and entered a sector where the shift is gentler and the measurements appear slightly altered. Despite their separation, the dual streams of information complement each other and grant scientists a more complete understanding of what the solar system's edge truly resembles. Right now, neither spacecraft dwells in the familiar realm sculpted by the solar wind, and neither floats entirely in the open galactic expanse. They're traversing a kind of transitional strip where the sun's protective bubble concludes, but the conditions still fluctuate enough that they don't seem wholly beyond it. It's not a sharp division the way preliminary sketches portrayed it. It's more like the final gossamer layer of a barrier that extends, undulates, and transforms depending on what's occurring inside the heliosphere and within the surrounding interstellar medium. Out here, the concentration of particles is extraordinarily sparse. When one of the spacecraft registers something a charged particle escaping from the sun, a cosmic ray wandering in from beyond, or a ripple in the magnetic field, it becomes noticeable precisely because the backdrop is so barren. But barren doesn't mean uncomplicated. This zone reacts to pressure variations originating from the sun, even from billions of kilometers distant. A powerful solar outburst can force the heliopause outward, and months or years afterward, the Voyagers will observe the consequences as a variation in density or a disturbance in the magnetic field. One of the unexpected findings both spacecraft have demonstrated is how irregular this zone proves to be. Voyager 1 witnessed an abrupt surge in cosmic rays when it penetrated the boundary, while Voyager 2 recorded a more progressive increase. That contrast informed scientists that the heliopause isn't configured identically in every direction. It warps, it indents, and it responds to whatever the sun and the galaxy are directing toward it. This peculiar region represents the first time we've managed to examine the point where the sun's dominance genuinely diminishes. It's delicate, it's subdued, and it changes in patterns that still perplex researchers. And even though both spacecraft are separated by vast distances, they're providing us a combined portrait of a location no mission has ever investigated firsthand. When people discuss the edge of the solar system, they typically reference the heliopause. It's the position where the solar wind exhausts its momentum and the material from outside the sun's sphere pushes back forcefully enough to halt it. For generations, it remained merely a hypothetical line sketched on diagrams because no one had ever journeyed there. The Voyagers became the first machines to arrive at it and actually experience what it was like. And what they discovered didn't align with the tidy illustrations. Voyager 1 was the first to reach the frontier in 2012. Before it crossed over, the solar wind surrounding it kept decelerating and the magnetic field started becoming more structured. Then the particle counts suddenly inverted. The quantity of high-energy cosmic rays streaming in from the galaxy jumped dramatically, and the lower-energy particles from the sun nearly vanished. It wasn't a gradual shift. It was more like stepping from one realm into another in a single instant. That sudden transformation told scientists the heliopause isn't progressive in that direction. It's more like a sheer precipice. Voyager 2 crossed 6 years afterward, and its encounter was distinct. The increase in external particles was slower. The magnetic field curved in a somewhat different orientation. The transition felt more like descending a slope rather than plummeting off a ledge. That told scientists the heliopause doesn't appear uniform everywhere. It expands, contracts, and buckles depending on which direction you approach it from and what the sun has been experiencing in the preceding years. Both crossings shared something fundamental. The measurements inside the heliosphere and the measurements outside bore no resemblance at all. Once each spacecraft stepped across, the environment transformed entirely. Outside the barrier, the plasma is more concentrated. Even though the area seems emptier, the magnetic field is more stable but oriented in a completely different direction. And the number of cosmic rays from the galaxy is substantially elevated because the sun's magnetic cocoon can't deflect them anymore. One of the aspects that captured researchers' attention was the way the boundary responds to events occurring far away. When the sun experiences a burst of activity, that surge of pressure eventually reaches the outer heliosphere. Months or years later, the Voyagers detect it. They register it as a sudden rise in plasma oscillations or as a spike in density. This revealed to scientists that the heliopause isn't locked in position. It breathes slowly across immense stretches of time, reacting to phenomena happening billions of kilometers away. Another revelation was the thickness of the boundary. Before the Voyagers reached it, numerous models predicted the heliopause would be thin, almost like the membrane of a bubble. But the spacecraft disclosed that it's broader and more intricate than anticipated. There are strata within it, zones where certain particles seep through, zones where magnetic fields twist, zones where the sun's influence fades unevenly. The greatest surprise was that interstellar space didn't resemble the tranquil void people presumed it would be. Instead of a silent, uniform environment, both spacecraft encountered pockets of turbulence, shock waves from previous solar events, and variations in particle flow that weren't foreseeable. That initial assumption that space outside the sun's bubble would be peaceful turned out to be mistaken. The crossing of the heliopause wasn't merely a landmark. It altered the fundamental comprehension of where the solar system genuinely ends and how the sun engages with the rest of the galaxy. But even after this accomplishment, Voyager's odyssey is only beginning. At their present velocities, each probe will require approximately 300 years just to reach the inner boundary of the Oort cloud, the enormous icy shell where the sun's gravitational influence finally begins to diminish, and it may demand another 30,000 years to traverse its farthest extents and finally depart our stellar neighborhood entirely. The heliopause itself demonstrated that the boundary is alive in a slow, ponderous way. It shifts, it responds, and it behaves differently depending on where you encounter it. One of the most unusual things the Voyagers identified after crossing the heliopause was how scorching the plasma becomes just outside the sun's bubble. When people first learned about this region, they imagined something spectacular because of how the figures were communicated. Temperatures of tens of thousands of degrees sound impossible, but temperature in space doesn't function the same way it does on Earth. The density is so minimal that even though the plasma is hot, there isn't sufficient material to actually incinerate anything. It's more like individual particles racing very rapidly through an environment that's otherwise nearly vacant. Voyager 1 detected the initial indications of this hot region when it transitioned into interstellar space. It recorded plasma vibrations that corresponded with the characteristics of extremely hot material. Later, Voyager 2 verified this same phenomenon but from a different direction, which helped scientists understand this wasn't a localized irregularity. It's a characteristic that envelops the heliosphere. The reason it forms relates to the manner in which the solar wind crashes into the material drifting through the galaxy. Inside the heliosphere, the solar wind streams outward at tremendous speed. As it presses against the interstellar medium, it decelerates and alters its form. The boundary isn't uniform. It's more like strata of compressed, elongated, and heated plasma. When the outward-moving solar wind collides with the incoming pressure from beyond, it generates a zone where particles get compacted together. That compression elevates the temperature. It's comparable to how air warms when it's forced into a smaller volume, but occurring on a scale so vast it's difficult to conceptualize. Both spacecraft found that this region isn't consistent. Some sections are hotter than others. Some sections are thicker. Sometimes the readings spike, and then a year later they decline. That told scientists this isn't a static layer. It shifts and reacts to what the sun is doing. A strong eruption of solar activity can dispatch shock waves outward, and when those waves arrive at the outer heliosphere, they strike this layer and heat it even further. The Voyagers capture these changes long after the events occur, because it requires months or years for the shock waves to travel that distance. Another thing that seized researchers' attention is how the magnetic field behaves in this zone. Instead of pointing in a smooth direction, it bends and contorts. Those contortions help trap and heat particles. They also make it harder for low-energy particles to move freely, which explains why the boundary behaves differently depending on where you cross it. Voyager 1 witnessed more sudden changes. Voyager 2 witnessed smoother transitions. That difference aligns with the concept that the hot plasma layer has uneven pockets. Even though this region is extremely hot, it's not hazardous to a spacecraft. The Voyagers don't sense anything in the conventional sense. The density is so low that the energy is dispersed across enormous volumes of space. What matters is what this layer reveals to scientists about the way the sun interacts with the galaxy. Before these readings arrived, many models assumed the heliopause was a clean line. Instead, it's more like a complicated buffer shaped by pressure, magnetic fields, and the slow push and pull of two competing environments. Understanding this hot layer helps scientists perceive the heliosphere as something that reacts constantly. Even though the changes happen slowly, it demonstrates that the edge of the solar system isn't a simple boundary. It's a place where two very different regions of space grind against each other. And the Voyagers, with instruments constructed in the 1,970 seconds, are the only probes that have ever been close enough to measure it. Even after almost 50 years in space, both Voyagers are still gathering data from the environment around them. The way the instruments were designed makes the readings straightforward. But that straightforwardness is exactly what makes them valuable. No other spacecraft has ever taken measurements from this far outside the sun's influence. So even basic numbers can teach scientists something new. One of the primary things the Voyagers still detect is the behavior of the magnetic field in their vicinity. Outside the heliosphere, the field isn't shaped by the sun the way it is inside. It follows the structure of the galaxy. And because the spacecraft are in two different directions, their readings help show how this field bends and shifts around the heliosphere. Voyager 1 often observes a more consistent magnetic direction, while Voyager 2 measures slight changes in turbulence. This difference helps researchers understand how the sun's bubble presses against the environment around it. Another measurement that still functions is the detection of plasma waves. The Voyagers can't directly measure plasma density anymore, but they can detect the vibrations that plasma makes when it's disturbed by passing shocks. When these vibrations sweep across the spacecraft, the instruments record them as small changes in frequency. Scientists can convert those frequencies into estimates of density. This is how they learned that the plasma outside the heliosphere is denser than they expected, and how they noticed it can change from one year to the next. Cosmic rays are another important component of the data. These high-energy particles originate from outside the solar system, and the Voyagers can detect them. Inside the heliosphere, the sun's magnetic field blocks many of these particles. Outside, the numbers rise sharply. By tracking those changes, researchers can see how much protection the sun provides and how that protection fades with distance. It also helps them understand how cosmic rays move through our corner of the galaxy. Even though the spacecraft is old, the particle detectors still pick up occasional increases in charged particles coming from the sun. These usually arrive months or years after the solar event happened, because it takes that long for the shock wave to travel outward. The Voyagers sense these distant echoes as bumps in particle counts or sudden stretches in the magnetic field. These delayed reactions show how long the sun's influence continues to spread even past the heliopause. The communication aspect fits naturally into this part of the story because it's tied directly to how the instruments work. At this distance, the signals sent back to Earth are incredibly weak. It takes more than a day for a message to travel from the spacecraft to the Deep Space Network antennas. The data rate is slow, and the engineers have to be careful about what they ask the spacecraft to send. Even so, each reading is still clear enough for scientists to extract information about the magnetic field, plasma behavior, and particle levels. It's not enough for detailed pictures or real-time analysis, but it's more than enough to track the environment around both probes. What makes these measurements meaningful is the fact that there is nothing else like them. No other spacecraft is positioned to check the state of interstellar space near the Sun. Even small changes in the data can reveal something about the structure of the heliosphere, the strength of outside pressure, or the long-term behavior of space between stars. Every transmission from the Voyagers adds another piece to a map that didn't exist before. Keeping the Voyagers alive has transformed into a long, careful balancing act. When they were launched in 1977, no one expected them to last anywhere near this long. The power sources on both spacecraft were designed to decay steadily, and over the decades, the available energy has dropped year after year. Because of that, engineers have had to make difficult choices about which systems stay on and which ones must be turned off for good. The radioisotope generators that power the Voyagers produce less electricity every year. At the start of the mission, there was enough power to run every instrument comfortably. Today, the energy margin is so thin that a single unnecessary system can drain more power than the spacecraft can spare. That's why NASA has spent years gradually shutting down heaters, backup circuits, and instruments that consume too much energy. It isn't because the science isn't useful. It's because keeping the spacecraft alive matters more than running everything at once. The heaters are one of the clearest examples. Many parts of both spacecraft are now operating at temperatures far below anything they were originally tested for. In some cases, components are colder than engineers ever believed they could survive, yet they continue to function. Instruments that were never designed to run without heat have kept sending data for years after losing thermal support. One of the most striking cases unfolded in May 2025 when the Voyager 1 team worked urgently to reactivate the spacecraft's primary roll thrusters, silent since 2004 after their internal heaters failed. By remotely toggling power switches, they were able to bring the thrusters back online just in time, preventing a potential fuel line rupture. It shows how remarkably robust the original engineering was, but also how delicate and uncertain the current situation has become. Another challenge is memory and data handling. Both spacecraft carry electronics built in the 1970 seconds, long before modern digital systems. Over time, cosmic rays strike the memory and corrupt bits. Engineers can sometimes correct these errors by rewriting the affected sections of code or reorganizing the memory map so the spacecraft avoids the damaged parts. Earlier in the mission, these problems were rare. Now they show up more often simply because the hardware is old and constantly exposed to high-energy particles in interstellar space. A clear example came in April 2025 when Voyager 1's team fixed a lingering flight data subsystem glitch caused by a corrupted chip holding just 3% of its code. Using instructions from 1960 era blueprints, engineers relocated the software to unused RAM segments, restoring full telemetry after months of garbled signals. Communicating with the spacecraft has also become more demanding. The signal strength is so faint that the Deep Space Network needs long sessions just to collect small amounts of data. The antennas on Earth must be aligned with extreme accuracy, and engineers have to plan every command around the long travel time. If a command creates a problem, it takes more than a full day to find out. That delay forces every decision to be slow and cautious. On top of that, in 2025, Deep Space Station 43 inches Canberra, the only antenna that can send commands to both probes, was undergoing upgrades from May until February 2026. This reduced the time available for communication in August and December, making careful planning more important than ever. Even the flight software itself has needed workarounds. In recent years, engineers found ways to reroute data paths inside Voyager 1 after it started sending back unreadable telemetry. This required digging into documentation written decades ago, and finding parts of the system that were never meant to be used in this way. These kinds of fixes aren't elegant, and they aren't simple. They're careful, targeted adjustments made by teams who understand that one mistake could end the mission permanently. The insulation around the wires has also aged. The temperature swings in deep space, along with the slow decay of onboard heat, have pushed the hardware far past its expected lifetime. Engineers can't repair anything physically, so they rely on creative solutions, switching to backup circuits, adjusting command timing, or reducing activity when the spacecraft shows signs of stress. Sometimes, the best fix is just doing less, giving the systems time to stabilize before sending the next instruction. Through all of this, the main goal has stayed the same: keep the spacecraft's key instruments working as long as possible. Voyager 1 now has only 3 working instruments: the magnetometer, plasma wave detector, and low-energy charged particle detector. Voyager 2 has the same 3, with its cosmic ray detectors set to shut down next year. These remaining instruments are crucial, giving us unique insights into the edges of our solar system. Every decision is made to protect them, so the spacecraft can keep sending back data that no other mission can provide. The fact that both Voyagers are still operating is a result of cautious engineering, careful decision-making, and a lot of patience. It's not luck. It's a slow, ongoing effort to keep 2 aging machines functioning in a place where they were never supposed to reach. And as long as the power holds, the measurements keep coming. When people talk about what lies ahead for the Voyagers, they often imagine a clean path leading out of the solar system. In reality, the journey is slow and divided into stages that stretch across enormous timescales. Both spacecraft have already crossed the heliopause, but that doesn't mean they've left the solar system in the full sense. The Sun's gravitational reach extends far farther than the heliosphere, and the region beyond it is more complicated than most diagrams show. The next major area the Voyagers will enter is the inner part of the Oort cloud. This isn't a thick region packed with ice and rock. It's mostly empty space, with occasional scattered objects drifting around the Sun at huge distances. The Voyagers aren't headed toward anything specific inside it, and the chance of them passing near an actual object is extremely small, but entering that region marks the beginning of the final stage of their solar system journey. Estimates suggest it will take a few hundred years before either spacecraft reaches the inner Oort cloud. Voyager 1 will reach it first because it's farther out and moving faster. Even though this part of space is quiet, it still sits under the Sun's gravitational influence. The Voyagers will continue to orbit the Sun in a loose, slow arc, unless something massive disturbs them, which is unlikely. Nothing about this stage involves sudden changes. The environment beyond the heliopause may shift slightly in density or magnetic behavior, but the spacecraft won't encounter anything that alters their paths in a dramatic way. For the most part, they'll drift steadily forward through a region that feels almost entirely empty. Over longer timescales, the outer Oort cloud becomes the final boundary. This is a spherical shell of objects that stretches so far from the Sun that a full orbit around the Sun could take millions of years. The Voyagers won't get anywhere near completing such an orbit. Instead, they'll travel in straight lines through a tiny portion of that distant cloud. By then, both will be silent, cold, and drifting without any functioning instruments. Once they pass the Oort cloud, the spacecraft will finally reach a point where the Sun's gravity no longer binds them. This is the moment when they truly leave the solar system, not just its magnetic bubble. It won't feel any different to the spacecraft, but it's a meaningful distance in terms of how the Sun interacts with the galaxy. Past that point, they become objects of interstellar space, moving among the stars without any connection to the place they came from. There's also the question of whether the Voyagers will ever come close to another star. Based on current trajectories, Voyager 1 will pass within about 1.6 light-years of a small star called Gliese, 445 inches, roughly 40,000 years. That isn't close enough for an encounter, but it's the nearest approach on its projected path. Voyager 2 will pass within a few light-years of another small star, Ross 248, on a similar timescale. These aren't flybys in the planetary sense. They're distant crossings, the kind where the spacecraft will be unnoticed and silent, drifting past with no way to report what they see. What makes the future path of the Voyagers interesting is how steady it is. Nothing dramatic happens. The spacecraft won't suddenly speed up or veer off course. They won't hit anything or fall into anything. They'll just keep moving forward, powered only by the momentum they've had since they were launched. The time frames are so large that the journey becomes more about perspective than events. They are slow, steady travelers moving through a region that no one will ever see firsthand. The Voyager's long future isn't about the data they'll send back, because that will end soon. It's about the fact that they will keep going long after every instrument is silent. Their path out of the solar system is a reminder of how big these distances are, and how small even the fastest spacecraft look when time is measured in thousands of years instead of decades. The Voyagers matter today for a reason that has nothing to do with nostalgia or the length of the mission. Their importance comes from where they are and what they're measuring. No other spacecraft has ever reached interstellar space. For decades, scientists built models of the heliosphere using indirect measurements from inside the solar system. Those models were useful, but they were guesses. The Voyagers turned those guesses into real numbers. They showed what the boundary looks like, how it behaves, and how it changes over time. That information reshaped the entire understanding of how the Sun interacts with the galaxy. They also matter because they opened up a part of space that used to be purely theoretical. Before the Voyagers crossed the heliopause, interstellar space for us was an idea, not a place. Now, it's a region with measured density, magnetic direction, plasma behavior, and turbulence. These details are the foundation for future missions that might one day follow. Without the Voyagers, those missions would be planning their routes blindly. With the Voyagers, they have a baseline, even if it's only 2 points in a vast environment. Another reason the Voyagers remain meaningful is the role they play in long-term solar studies. The readings they send back are more than interesting science. They help confirm how far the Sun's influence reaches and how much protection it offers from cosmic rays. Inside the heliosphere, we're shielded from most high-energy particles. Outside, the levels are much higher. Tracking those differences helps researchers understand radiation risks for any future spacecraft that might travel out of the Sun's protective bubble. Their survival also shows the value of engineering that doesn't rely on modern complexity. The Voyager's instruments are simple by today's standards, but that simplicity is why they still work. They were built with enough margin to handle unknown conditions, and that approach keeps paying off decades later. It's a quiet reminder that exploration doesn't always require cutting-edge hardware. Sometimes it requires durability and patience. And there's another part that scientists don't ignore. The Voyagers are markers of where we have been. They hold the first direct measurements of the heliosphere's edge, and those measurements will remain the reference point for a long time. Even when the spacecraft goes silent, the data they've already sent home will continue to be studied. The field of heliophysics will keep returning to their readings whenever new questions come up about how the Sun interacts with the material around it. They also stand as the first objects built by humans to enter interstellar space. That fact doesn't add scientific data, but it does mark a boundary in human activity. The Voyagers weren't designed to be symbolic, but their survival and distance give them meaning. They're proof that a machine built for a simple tour of the planets can end up far beyond its original purpose, still doing work that no newer probe can replace. And finally, they matter because their data closes a gap that nothing else can fill right now. Every transmission from either spacecraft, no matter how small, adds to a map of the outer solar system that never existed before. Even a weak signal that takes more than a day to reach Earth carries information about a place no one has ever visited. That alone makes the mission valuable. When you look at where the Voyagers are now, it's easy to forget how ordinary their beginnings were. They were built for a specific mission that was supposed to last only a few years. Once the planetary tour was over, there wasn't a plan for anything beyond that. They were expected to drift quietly with no real role left to play. Yet, instead of fading into the background, they ended up in a place no one had mapped, measuring things no one had ever seen, and sending back information that keeps changing how scientists describe the solar system. The interesting part is how normal the spacecraft themselves look if you strip away their distance. They aren't advanced machines. They don't adjust themselves. They don't have backup systems designed for the environments they've entered. They're old hardware running on limited power, carrying instruments that were never meant to operate at these temperatures. And still, after all this time, they continue giving readings that help answer questions people didn't even know how to ask in the 1,970 seconds. Thinking about their situation now puts the scale of the solar system in perspective. The Voyagers have been moving for nearly half a century, and they've only just stepped outside the Sun's magnetic bubble. If you compare that distance to the size of the Oort cloud, or the time it will take to eventually drift beyond it, you start to see how slow the process is. Space doesn't open up in clean stages. It stretches out in long, quiet distances that don't feel real until a spacecraft reaches them. Another thing that stands out is how consistent the mission has been. There were no moments where the Voyagers suddenly changed direction or encountered something that altered their paths. Everything has been steady. They keep moving forward. They keep sending whatever data they can, and they keep outliving the estimates that try to predict their limits. That slow reliability is part of what makes the mission notable. It isn't dramatic, it's patient. At some point, the transmissions will stop. There won't be a final message or a last observation to mark the end. The spacecraft will fall silent gradually as the power drops below what the hardware needs. After that, they'll continue drifting with no connection to Earth and no sign that they were ever part of a mission. They'll simply exist as objects traveling through a region of space that almost nothing else from our world has reached. What remains after the signal fades is the record of what they've already sent back. The measurements of the Heliosphere, the data from interstellar space, the slow changes in magnetic direction, the detection of the hot plasma layer, all of it becomes part of the long-term understanding of how the Sun fits into the galaxy. The Voyagers won't be active when the next generation of missions reaches this region, but their numbers will still be in the background, shaping expectations and helping researchers interpret whatever comes next. And maybe the simplest part of the story is this. The Voyagers show how far steady motion can take something when you give it enough time. They weren't built for this stage of the journey, but they reached it anyway. They weren't designed to study interstellar space, but they're the only machines doing it. They keep moving, not because of pressure or purpose, but because nothing is stopping them. That quiet momentum is the last thing they'll carry as they leave the solar system behind. One small step at a time. The machinery inside both spacecraft tells its own story about endurance. Every component, every wire, every sensor was built during an era when personal computers didn't exist and the word internet hadn't been invented yet. The engineers who assembled these probes worked with slide rules and paper blueprints. They calculated trajectories by hand and tested components in conditions they could only estimate. And yet, those same components are still functioning in an environment more hostile than anyone fully anticipated. The plasma wave instruments, for instance, weren't designed to operate in true interstellar space. They were meant to study the environments around planets, to measure the interactions between planetary magnetospheres and the solar wind. But when the spacecraft crossed into the region beyond the heliopause, these instruments adapted. They began detecting vibrations in a medium no one had directly measured before. The frequencies they recorded told scientists about density, about temperature, about the way shocks propagate through a space so empty that calling it a vacuum barely captures how little matter exists there. The magnetometers have been equally revealing. These devices measure the strength and direction of magnetic fields. And in interstellar space, they've shown that the galaxy has its own magnetic structure. It doesn't follow the Sun's influence. It has its own orientation, its own fluctuations, its own story. By comparing the readings from Voyager 1 and Voyager 2, scientists have started to piece together a picture of how the galactic magnetic field wraps around the heliosphere, how it compresses the Sun's bubble in some directions and allows it to expand in others. The charged particle detectors have been tracking the influx of cosmic rays, particles accelerated to enormous speeds by distant supernova explosions, colliding neutron stars, and other violent events scattered across the galaxy. Inside the heliosphere, these particles are partially blocked by the Sun's magnetic field. Outside, they flood in with much greater intensity. By measuring this difference, the Voyagers have helped scientists understand the radiation environment that any future interstellar mission will have to navigate. It's not just academic, it's practical. If humanity ever sends a probe to another star, the data from the Voyagers will be part of the foundation for designing that mission. The longevity of these instruments is almost miraculous when you consider what they've endured. Temperature extremes that swing from scorching heat near the planets to the deep cold of interstellar space. Radiation bombardment from cosmic rays and solar particles. Decades of continuous operation without any physical maintenance. And through it all, they've kept working. Not perfectly, not without glitches and failures, but well enough to keep sending back meaningful data. The way the mission has been managed also deserves attention. The team of engineers and scientists who monitor the Voyagers has changed over the years. People who were young researchers when the spacecraft launched are now retired. New generations have taken over, learning from the old documentation, mastering the quirks of hardware they've never physically touched. The institutional knowledge required to operate these spacecraft is vast and fragile. Every decision, every command sequence, every workaround has to be documented and passed along because there are fewer and fewer people who remember how the systems were originally designed. This transfer of knowledge has become part of the mission itself. It's not just about keeping the spacecraft alive. It's about preserving the ability to communicate with them, to understand what they're telling us, to make informed decisions when problems arise. And problems continue to arise. In 2023, Voyager 2 experienced a communications blackout after a routine sequence of commands inadvertently caused the spacecraft's antenna to shift slightly away from Earth. For weeks, the spacecraft was unreachable. Engineers couldn't send commands. They couldn't receive telemetry. They could only wait and hope that an automated reset would eventually realign the antenna. And it did. After an agonizing silence, the signal returned, and the mission continued. That incident highlighted just how precarious the situation has become. These spacecraft are operating at the absolute edge of what's possible. Every command carries risk. Every system that fails is one more step toward the inevitable moment when communication will be lost forever. But until that moment comes, the mission continues to yield discoveries. In recent years, scientists have used Voyager data to study how the heliosphere responds to the solar cycle. The Sun goes through an 11-year cycle of activity, moving from solar minimum, when the Sun is relatively quiet, to solar maximum, when sunspots, flares, and coronal mass ejections are common. These cycles affect the solar wind, which in turn affects the shape and size of the heliosphere. The Voyagers have been outside long enough now to observe how the heliopause shifts in response to these cycles. It breathes, expanding and contracting over years, reacting to the changing pressure from the solar wind. This dynamic behavior was predicted, but the Voyagers have turned prediction into observation. They've shown that the boundary isn't static. It moves. It flexes. It responds to forces originating billions of kilometers away. Another area of study involves the local interstellar cloud, the region of space the Sun is currently moving through. This cloud has its own properties, its own density, its own magnetic field. The Voyagers are measuring these properties directly for the first time. Before now, scientists could only infer what the local interstellar medium was like by studying light from distant stars and making educated guesses. Now they have direct measurements. They know the density. They know the temperature. They know the magnetic field, strength, and direction. This information is crucial for understanding not just our immediate surroundings, but also how stars interact with the interstellar medium in general. The Sun isn't unique. Every star has a heliosphere, a bubble carved out by its stellar wind. By studying the Sun's heliosphere in detail, scientists can make better predictions about how other stars interact with their environments. The Voyagers are also helping to refine models of how the solar system moves through the galaxy. The Sun orbits the center of the Milky Way, and as it does, it passes through different regions of the galaxy. Some of these regions are denser than others. Some have stronger magnetic fields. The properties of the local interstellar medium change over millions of years as the Sun moves through different neighborhoods. By measuring the current conditions, the Voyagers are providing a snapshot of what this particular moment in the Sun's galactic journey looks like. And there's a philosophical dimension to all of this. The Voyagers represent humanity's first physical presence in interstellar space. They carry golden records, time capsules filled with sounds and images from Earth, messages intended for any intelligent beings who might one day find them. The likelihood of the records ever being found is vanishingly small. The galaxy is vast. The Voyagers are tiny. They're moving slowly on a cosmic scale. But the gesture itself has meaning. It's a declaration that we were here, that we looked outward, that we wondered what else might be out there. The golden records contain greetings in dozens of languages, music from different cultures, images of life on Earth, diagrams showing our location in the galaxy. They're not meant to be practical. They're meant to be symbolic. And, in a way, the Voyagers themselves have become symbols. They represent curiosity, persistence, the willingness to send something into the unknown with no expectation of return. They weren't built to come back. They were built to go as far as they could and to tell us what they found along the way. And they've exceeded every expectation. When you think about the sheer improbability of their success, it becomes even more remarkable. They were built with 1,970 seconds technology. They were launched on rockets that had only recently become reliable. They flew past planets where the radiation nearly fried their electronics. They survived impacts from micrometeorites. They endured temperature swings that should have cracked their structures. And they're still going, still sending data, still teaching us about a part of the universe we've never touched. The fact that both spacecraft are still operational is a testament to the people who designed them, the people who built them, and the people who have kept them alive for nearly 5 decades. It's also a testament to the value of simplicity. The Voyagers don't have complex software that can crash. They don't have delicate systems that require constant adjustment. They have simple, robust instruments that were designed to last. And that simplicity has proven to be their greatest strength. In an age where technology becomes obsolete in a matter of years, the Voyagers stand as a reminder that sometimes the old ways work best. As the mission enters its final years, the focus has shifted. It's no longer about exploring new planets or making groundbreaking discoveries every few months. It's about extracting every last bit of information from the environment the spacecraft are in. Every measurement matters. Every data point adds to the picture. And every day that the spacecraft continue to function is a victory. The engineers know that time is running out. The power levels are dropping. The instruments are aging. The communication windows are shrinking. But they also know that as long as the Voyagers are alive, they're providing information that can't be obtained any other way. And so, they continue to monitor, to adjust, to problem solve, to squeeze every possible moment out of a mission that was supposed to end decades ago. And when the end finally comes, when the last transmission is received and the spacecraft falls silent, the legacy will remain. The data will still be there, archived, studied, referenced for generations. The images from the planets will still inspire. The measurements from interstellar space will still inform, and the Voyagers themselves will still be out there, drifting through the darkness, carrying their golden records, moving farther from home with every passing second. They'll travel for millennia. They'll pass near other stars. They'll journey through regions of space we can barely imagine. And they'll do it in silence, no longer able to tell us what they see, but still moving, still exploring, still representing the best of what humanity can achieve when we dare to reach beyond our world and into the cosmos.